Okay, here we go. We're going to begin review number 2. This one says Jack's bowling score was 20 less than twice Jill's score. The sum of their scores was 205. What was Jack's score? What I want you to take away from this problem is, as we're reading the sentence in the description, it seems like there are two numbers that we don't know, right? And then they're only asking us for one of them. They're asking us, what is Jack's score? So I'm going to go ahead and call that X. Sometimes I may use another variable like J, but because it mentions Jack and Jill, that's going to get too confusing. So I'm going to call Jack's score X. And they didn't mention Jill's score, so I'm going to call that one Y. Okay, so we have Jack's score and Jill's score. Now, Jack's score, that's X, was, that's almost like saying it is, or it was, that's like it's equal to 20 less than twice Jill's score. Now, 20 less than something means we're going to be taking away 20 from something. So something minus 20. We have to look after that phrase to see, well, what did we take 20 away from? 20 less than twice Jill's score. Okay, so I called her score Y, so twice that would be 2Y. So Jack's score X is equal to 2Y, twice Jill's score, minus 20, because it was 20 less than twice her score. Then it tells me the sum of their scores was 205. That just means if we add those two things together, we get 205. So if I add his score and her score, X plus Y, I get 205. What was Jack's score? So we got to figure out a way to get X by itself. This is a system of equations because there are two variables that we don't know the value of, but we have two equations we can use to solve them. And I want to remind you that there are a couple algebraic strategies we've seen with this. One of them is called substitution. That's when you sort of have one of the variables by itself already, and you know how to write it in terms of the other variable. And then the other way is if both equations are in standard form, like if we had two equations that both had X's and Y on the same side, maybe something like this. And I'm just making up a number here. But if we had two equations like this, then we would maybe use elimination. That's where you multiply one of the equations or even both of the equations by a number, sometimes a positive, sometimes a negative. And then you combine the equations, you add them up so that one of the variables cancels out, and whatever variable is left, you'll be able to solve for, and then you can go plug it back in. But the two equations we have are X plus Y equals 205 and X equals 2Y minus 20. Well, this is good news for us if we want to use substitution, because we already know that the X by itself can be replaced or is equal to 2Y minus 20. So what I'll do is I'll take this equation right here. Let me highlight it. I'm going to take this equation and I'm going to rewrite it, but without using the X variable. I'm going to replace X with 2Y minus 20 because those two things can be swapped for each other. They can be substituted because they're equal. So if I do that, don't have a ton of room to write this out, but let me maybe put it up here to the over here. I would take X plus Y equals 205. And I'm going to take the X out, and in its place, I'm going to put 2Y minus 20. Then we keep the rest of the equation exactly the same. 2Y minus 20 plus Y equals 205. There was nothing in front of the X, so I don't need to distribute or multiply anything here. But I can combine some terms. So 2Y plus another Y makes 3Y minus 20 equals 205. Then I would add 20 to both sides. That's going to leave 3Y equals 225. And then I'm going to divide by 3 to get rid of the number in front of the Y. Then I've got to divide 225 by 3. I'm going to do a basic division out here to the side, since this is supposed to be done without a calculator. So 3 doesn't go into 2. It goes into 22 7 times. 7 times 3 is 21, so there's 1 left over. Bring down to 5. 3 goes into 15 5 times exactly, because 3 times 5 is 15. There's nothing left over, nothing else to bring down. So I'm done. I get 75 for Y. Okay, so Y equals 75. Then I'm going to take this number. There's one of my solutions to this system. So I know one of the values of the variable Y. Now I need to know the value of X. So to do that, I just plug 75 back into either one of these equations. Since I have an equation that tells me X equals 2Y minus 20, I'm going to use that one. So x would be 2 times y, which I know is 75 now, minus 20. 2 times 75 is 150 minus 20. And if I do 150 minus 20, that's 130. So x is 130 and y is 75. If I wanted to double check that, I could also take those numbers and just go add them up over here. And 130 plus 75 does make 205. That works. So I know x and y. And now just make sure we answer the right question. What was Jack's score? Because at the very beginning, I laid out that x was Jack's score. That just tells me right away, okay, Jack got a 130 because he was the x. Okay. Let's move to number 2. Here's another system, right? When you see this little symbol right here drawn in front of 2 equations, that's usually telling you those work together as a system. This is another example where we have one of the variables on one side by itself, and then the other variables and numbers are on the other side, like right here. So this kind of lends towards substitution. Okay. Now, there is something kind of unique about this one that I like. I could try to get the x all the way by itself by dividing both sides by 3. If I did that, I would get x equals 2y over 3, which is 2/3 y, minus 10 divided by 3, which is 10/3. So I could do that and I get fractions here. Then I could go plug this in for x to the other equation, do substitution there. But this is a sort of a cooler way to do this problem. Notice how we know that 3x equals 2y minus 10, and there's a 3x in the other equation. So we don't actually have to finish solving for x all the way. We can just replace 3x with 2y minus 10 in the other equation. So that's exactly what I'm going to do. Where it said 3x plus y equals 14, I'm going to take that 3x out and in its place put 2y minus 10, because that bottom equation tells me those two things are the same. They're both equal to each other. Then I keep the rest, plus y equals 14. So if I combine like terms, that gives me 2y plus another y is 3y minus 10 equals 14. Then I'll add 10 to both sides. I'm gonna have to write out a little bit to the side here now. That gives me 3y by itself equals 14 plus 10 is 24. Divide both sides by 3. And we get 24 by 3 divided by 3, which is 8. That's my y value. If I wanted x, I could just go plug it back in right here and then simply solve. But notice this problem just wanted the value of y. So we already have it. Y equals 8. Okay, number 3, we did this one in class, but I'll quickly go through it again. We're supposed to graph this quadratic. A couple things I know right away looking at it. It's in standard form. It's not factored. And in standard form, because we have positive x squared, I know it's going to have this shape. It's going to open up with the arms extending up. And I also know the y-intercept is that number at the end that doesn't have any x's. So my y-intercept is negative 18. Now they don't really give me a scale here, so I'll have to make my own. And if I count by ones, I definitely won't reach negative 18. So let's maybe count by, I don't know, 3s or something. 3, 6, 9, 12, 15, 18. So this will be where negative 18 would be. Okay. I'm just going to write the coordinates here, 0, negative 18. Second thing is, I would want to know what the zeros are. So I would factor this if I could. So x squared minus 3x minus 18. Can we factor that? I'm going to draw an area model. Put x squared in the first box. This one needs 4 squares because it does have a number by itself. That goes in the bottom right. My diagonal product is then negative 18 times x squared, which is just negative 18x squared. And then I want to find factors of that because the other diagonal product also must be negative 18x squared. Now, because I have minus 3x, that means I need more negatives than positives. So when I list my factors, I want to consider the negative ones as the bigger values. So 1 and negative 18, 2 and negative 9, 3 and negative 6, that's going to be the 1. Because 3 take away 6 would give me negative 3. So let's go put those in our model. And now we factor the outside. Looking across the top, the only thing those have in common is x, and x times x makes x squared. I would need a negative 6 above the negative 6x, positive 3 out beside the positive 3x, and just double checking 6 times negative, or excuse me, 3 times negative 6 gives me negative 18. That works. So factored form is x plus 3 times x minus 6. So why would I put this in factored form? Because if I set the factored form equal to 0, that gives me the zeros of the graph, the places where it crosses the x-axis. So let's see what numbers we could plug in to make those factors equal 0. Well, what plus 3 is 0? That would be negative 3. What minus 6 equals 0? That would be positive 6. So now I'm going to go through and draw these. I'll keep the scale at 3 so that both x and y have the same scale. 3, 6, 9, 12, 15, 18. 3, 6, 9, 12, 15, 18. Okay, so negative 3, if I'm counting by threes, would be right there. Negative 3, 0, and positive 6 would be right there. 6, 0, and then my quadratic is just going to come down through this one, go through here. Now, I am going to double check and see where the vertex would need to be. The vertex is always halfway between the zeros. And to get that halfway point, you add them up and divide it by 2. You basically average them. So if I took negative 3 plus 6 and divided that by 2, that's my, what we call the axis of symmetry. That's the x value where you have the middle of the graph. So that's going to happen at x equals negative 3 plus 6 divided by 2, which is positive 3. Negative 3 plus 6 is positive 3. And then divide that by 2 and you get 1.5, 1.5. So somewhere right here, halfway between 0 and 3, that's where the vertex would be. So this graph is going to go a little bit lower, then it's going to turn and come back up, keep going up, and look something like that. Okay. Let's go to number 4. The rocket coaster has 15 cars, some that hold 4 people and some that hold 6 people. There's room for 72 people altogether. How many 4-passenger cars are there? So here's our question. How many 4-passenger cars are there? Let's call that X. How many means we're looking for a number of 4-passenger cars. And then they mentioned that some hold 4 and some hold 6. So that means we also don't know the number of 6-passenger cars. I'll call that Y. So here's another systems problem. This is actually very similar to the Jack and Jill bowling score one, right? 2 numbers, we don't know what they are. Let's go through and let's make sense of this. The rocket coaster has 15 cars. That's a total number of cars. And I know some of the cars are X, some of them are Y, but together the total must be 15. So one of my equations is just going to be X plus Y equals 15. Okay. Now, this is a little different from the Jack and Jill one because in the number 1 problem, they told me how Jack's score compared to Jill's, right? It was 20 less than twice her score. This one doesn't do that. It doesn't tell me like the number of 4-passenger cars is 5 more than 3 times as many 6-passenger cars. They don't give me anything like that. All they do is they say there is room for 72 people altogether. So is there a way I can represent like how many people each car is worth or each car can hold? And there is. If X is the number of 4-passenger cars, every one of those cars, every one of those X's holds 4 people. So the number of people in all of those cars would be 4 times X, right? So for example, if X was 2, if we had 2 of those cars, do 4 times 2 and you would get 8 people total in those cars. But each of those holds 4, and each of the Ys, each of the 6-passenger cars holds 6 people. And when we put all the people together, there are 72. So now this is a system. Neither of the variables is solved for yet, but we could either solve one or we could try to use, and if we solved one for X or one for Y and plug that in, that would be substitution, or we could try the elimination method. That's actually what I want to do. I want to try elimination with this one. So I need to either eliminate the X's by having the same number, just 1 positive, 1 negative, or eliminate the Y's, same number, 1 negative, 1 positive. I can make the same number of either one of them pretty easy in this particular equation, but I'm going to cancel out the X's, I think. And then I'll go back and cancel out the Y's or solve for, or once I've canceled out the X's, I'll solve for Y and then go plug that value back in to find X. So how would I get the same number of X's and just make sure one is positive and one is negative? This one's pretty easy. Take the top equation and just multiply it by -4, because -4 times x would make -4x, and that will cancel with the positive 4x down here. But we have to distribute that -4 to everything in the top equation. -4 times plus y is -4y, and then equals -4 times 15 is -60. Okay, because 15 times 2 is 30, and then do another 2 more, and that would be 60. All right, then keep the bottom equation exactly the same. We don't have to multiply it in this case, because just changing the top equation by multiplying everything by -4 gives me enough. So now I can combine these equations and the x's eliminate. -4x cancels positive 4x. Now combine the y's. -4y plus 6y makes 2y. And -60 plus 72, think about that like 72 minus 60, that leaves 12. So if I divide both sides by 2, 12 divided by 2 is 6. So there are 6 y's, or excuse me, y is 6. There are six passenger cars. And if I know that, and I remember that, wait a minute, there were 15 total cars. Remember, x plus y equals 15. I'm going to take this 6 and plug that back in for y. So x plus 6 equals 15. That means you just take away 6 from 15. And whatever's left must be the 4 passenger cars. 15 minus 6 is 9. So that's going to be the answer to our actual problem here, because it asked how many 4 passenger cars were there. We've got 9 of them. Okay. All right, last one, number 5. If y equals 3 to the x is replaced with y equals 3 to the x plus k and results in this function, graph to the right, determine the value of k. So notice what they've done. They didn't change the variable where the x was. Remember, sometimes we've seen where you will have something and you'll put parentheses around the x with like a +2 or a -5 or something like that in a function. And we said that if it's beside the x like that, then that moves the graph left and right. But if you add something on the end, like plus k, then that slides the graph up and down. So in this case, this plus k, they stick on the end. All that means they've done is they've shifted the graph either up or down. Now, the type of equation they gave us was y equals 3 to the x. That is exponential because the x is in the exponent, right? The x is the exponent. That means it's exponential. So exponential graphs, if the number that you have with the exponent, in this case, the base, the 3, if that's bigger than 1, it's going to grow. It's going to curl up and to the right. Start flat and go up, like we see this shape right here, okay? Exponential growth looks something like that. If that number was less than 1, like a fraction or a decimal, then it would go the other way. It would curl down and flatten out. But that's not what we have here, so we do expect growth. Now, another thing we need to know is that with exponentials, where is the y-intercept if we don't see some particular number written? Well, remember the form for exponential equations. It's usually like something times something else to the x power. Well, we can tell that our b number here is 3, but we don't see a number in front of the 3. So what would this a value be? Well, if you don't see one, that means it's just a 1, because multiplying by 1 wouldn't change 3 to the x, but that still means a actually is 1. And that a value is the y-intercept. So normally the y-intercept on an exponential growth graph, if you don't change the y-intercept by multiplying by something other than 1, then your y-intercept is just 1. Plug in 0, you get 1. And the reason that's true is because anything to the 0 power, if we do 3 to the x of 0, anything to the 0 power equals 1. So that means since y equals 3 to the x, if x was 0, then y would just equal 1. So that's our normal y-intercept. I want to put that over here on the graph. That's the normal y-intercept. But this graph actually has a y-intercept way down here, and it was shifted down. That means we subtracted some number from this. So let's just count and see how many. So 1, 2, 3, 4, 5. So this must be y equals 3 to the x minus 5. Okay. Because the only way to get a negative value here for your y-intercept is they have shifted this graph down. They couldn't have multiplied by a different number. Otherwise, that would change the shape of the graph. You can technically get a larger y-intercept by just multiplying. Like, let's say we wanted the y-intercept to be 2. We could have just said y equals 2 times 3 to the x. But that doesn't work with negative y-intercepts, okay? Because that would also flip the graph kind of upside down and the shape would change. But in this case, the k value must have just been 5. So that's the takeaway I want you to have for this. If you have a function and you add or subtract some number on the end, that's going to slide it up or down that many values. Okay. If you have plus some number, it's going to go up that much. If you have minus some number on the end, it goes down that much. If you have a change inside of the parentheses, like if the exponent had said 3 to the x plus k, well, that wouldn't move it up or down. That would move it left or right. So in this case, if you have a plus k in the parentheses with an x like this, that's going to move it left by a distance of k. If you have minus k, that's going to move it to the right. We've talked about that, how it's kind of opposite of what you think. And then the other type of change is what happens if you just multiply the whole function by a number, and that's going to make it taller or shorter. And usually that makes it look skinnier or wider. If you stretch it taller because you multiplied by something bigger than 1, then it gets skinnier looking. If you multiply it by a fraction or a decimal, something smaller than 1, it's going to get shorter and make it look wider when you're looking at the graph. Okay. But in this particular problem, the value of k must have been -5. That's how far the y-intercept shifted down. All right, that's it for review number 2. If you have any questions, just send me an email.